Hi to everyone, I'm Andrea Fioraldi, a master's student from Sapienza University of Rome, and with me there is Dominik Maier from TU Berlin, and today we'll talk about AFL++, combining incremental steps of fuzzing research. American Fuzzy Loop, or AFL, is one of the most powerful and used coverage-guided fuzzers that we have as open source software. If you don't know what is coverage-guided fuzzing, it's a software testing technique that aim to mutate inputs for a program under test that is typically instrumented, looking for crashes. It also says interesting input that increase the code coverage seen so far in the program under test. AFL is a widely used tool and discovered many vulnerabilities in softwares. It is also a baseline for a lot of fuzzers that are based on FL from both academic research and industry. But this tool is not anymore updated with new features from 2017. So there is a lot of interest in this tool. And why not fork it to continue the development? As I said, a lot of research and new techniques and new fuzzers are based on FL. There are also works that try to deal with the problem of the fuzzing roadblocks that are particular constructs in the code that makes the exploration of the code coverage by the fuzzer hard. There are works like Laffenthal based on augmenting the feedback to the fuzzer and with the progress of a comparison, and also other works like Red Queen or User or other fuzzer that guess which part of the input affect a comparison and try to replace the token extracted from comparison into the input using what is the so-called input-to-state mutation. Other works try to improve the mutation strategy of FL, like FL Smart that introduce a mutator that is based on the virtual structure of the input file format that adds the capabilities of a structured fuzzer to FL. This is done to avoid the fuzzer to generate almost every time an invalid input and to stress so deep paths that are behind the parsing stage of a program. There are also very important works that try to enhance the speed of the fuzzer. That is a very important factor. There is, for instance, InStream that try to reduce the number of instrumental program points to reduce the overhead of the instrumentation. Also PTFL that try to implement a snapshot syscall on top of Linux to avoid fork, that is a very expensive syscall for snapshotting. There is also work that try to inline the instrumentation in screen mode and enable the translation block linking, having a speed up in QEMU that is comparable to FL GCC. But from the point of view of a security researcher, the combination of these techniques is not trivial, it's a huge problem, because typically these new techniques are implemented forking FL of another fuzzer, and so they are developed orthogonally, and they are not easily combinable without a huge effort in development. These tools are also often not maintained anymore after the publication of the relative paper, and some of the techniques like Red Queen are also not even implemented on top of FL, so an analyst has to rewrite from scratch the technique if you want to combine it with another technique. Another problem for security analysts is that if an analyst creates a new fuzzing technique, he may want to cross-compare this new technique to the previous works that are the state-of-the-art in fuzzing, that are theoretically compatible with this technique. This is often really needed to assess the real effectiveness of a new technique. For instance, if I implement a new type of coverage that better approximates the program state than code coverage, I may want to cross-evaluate it with different roadblock bypassing techniques, like Red Queen or Laffenthal that we have seen so far. If I have to do so, implemented my new technique on top of a lot different fuzzers, this is of course a huge waste of time in terms of development of the technique. So here comes AFL++ to deal with these problems that security analysts may have. That is our new AFL fork that we are developing and maintaining as an open source software. So we integrate previous works based on AFL in our code base and often re-implement from scratch techniques that are not implemented on top of AFL or which the code base doesn't meet our requirements in terms of quality of code in a single framework that is AFL++. We use the combination of these techniques to research about new insights in fuzzing and use these new findings in order to improve the fuzzer, to make it better and better. We also, of course, do some research about fuzzing and we try to create new techniques in the frameworks, not only implementing previous works. Now we let to speak Dominik, that will introduce to us a bit of features and capabilities of this fuzzing framework.
Thank you, Andrea. So let's get into AFL++. The main point that we were focusing on the whole time is the usability. We think AFL has great usability. Everybody knows how to use it. It's command line driven and is pretty clear. So for all new features that we integrate, we try to stick as closely as possible to AFL while adding new flags where necessary and while changing defaults around so that they can be very convenient for the user. However, we not only focus on the end user, but also we try to make it easy for researchers to implement their ideas. So they're one step below the command line. They have to use the C bindings or Python bindings to custom mutators. But using our Custom Mutator API, they can implement most of the research out there without even touching or changing a single line in AFL++. So it's no longer needed to fork AFL each time, but for most cases, you can just implement some of these functions. Custom fuzz for building the whole fuzzer from the ground up. Custom post process to inject data or change data right before it reaches the target. For example, this can be used to add structured fuzzing to your fuzz cases. Custom trim to add trimming. Custom habit mutations to add just different mutations. And then you can also interact with AFL's queue using queue_get and queue_new_entry. So these are callbacks that you can then use to hook things that happen inside the fuzzer. Using this Custom Mutator API, you can build almost all new tooling on top of the already existing research and then mix and match them. So you can also have more than one custom mutator in a run for AFL++. On top of usability enhancements, we also put a lot of engineering effort into AFL++ and added the more abilities to mix and match different things. So for example, we have a variety of different instrumentations, especially for binary only targets. And on top of them, we added some features that have only been present in the normal gray box world. So what we did was we added something similar to the LAF Intel LLVM pass to QEMU and Unicorn mode. So we can split comparisons in while running inside the emulator. And we have a lot of different backends using, for example, we have QBDI as a backend. And also we have different plugins for GCC, LLVM mode, and still support, even though it's deprecated, AFL GCC, the old school target. So why do we still support AFL GCC, you may ask? Well, Our mantra is that AFL++ should run on as many platforms as possible, because you should be able to fuzz all the things. So what we have ported AFL to is not only GNU Linux, but also Android, iOS, macOS, FreeBSD, OpenBSD, NetBSD, Illumos OS, Heiko, and Solaris. And we're proud that it's already packaged in some popular distributions like Debian, Ubuntu, NixOS, Arch, Linux, FreeBSD, Kali, and so on and so forth. So yeah, we are taking over the whole Unixoid system. Coming back to what we call cross evaluations. This is the main point that AFL++ allows you to do, is you can use any of the implemented features in together with each other. And in the paper that we present today, you can read up on some possible examples that have different outcomes. So you can see that if you combine Ngram4 with MOPT, the performance can differ vastly from leaving out MOPT, for example, or for Red Queen, sometimes it improves, sometimes it gets worse. For example, here you can see in libpcap that Red Queen improves the performance by a lot. But on top of that, MOPT improves it even further. So the normal MOPT is really bad in comparison to Red Queen, but if you add both of them, then you get a really good fuzzing performance. However, on the other targets, for example on Bloaty from Fuzzbench, you see that Red Queen performs pretty bad. It is actually the worst performing for the first few hours, while MOPT alone performs a lot better. So here Red Queen drags the whole performance down instead of improves it. There are also other examples in the Fuzzbench results where MOPT would, for example, not improve the performance overall. So specifically targeted towards the Fuzzbench runs, what we do right now is we optimize, handpick each individual fuzz case. What you can see is to get an optimal configuration, you need to run the fuzzer for a bit, observe several runs of AFL++ in different configurations, and then afterwards you can see where the blind spots are and select the best combination of features. Of course, this is some sort of over approximation because we can't really say in advance what to do. So what we plan to do for the future is we want some sort of static analysis. So we want to have prior knowledge about the target and see that this specific setting may be beneficial. Like Red Queen may be beneficial if you have lots of strings in the binary and so on and so forth. Of course, right now we use the normal AFL scaling approach, which is just start many instances of AFL and they will synchronize over the file system. What we try to do right now is implement a scaling approach that just does normal threading internally. And we have a plugin system coming up that not only allows custom mutations, but allows you to implement your whole fuzzer using our little building blocks. Lastly, we are working on a novel instrumentation method that is completely collision-free. Right now you have collisions in AFL++ maps because some of the basic blocks are hashed in a way that they collide, that the addresses collide, and we can do it completely without collisions in the future. So to wrap this up, I will give back to my colleague Andrea for a quick moment to show you AFL++ in action. Andrea?
Now I'll show you how to combine some of the variable techniques into AFL++ using TCP dump as a sample target in QEMU mode. I start with simply running the fuzzer in default mode, that is like running normal AFL but faster. Then, for instance, we can resume the execution adding a schedule, for instance, rare, that give more time in fuzzing test cases that execute paths that are deeper and not stressed frequently by the fuzzer. We can also add, for instance, MOPT to schedule the mutations. Even add, on top of that, a roadblock bypassing technique. In this case, compare coverage level tray, that means that also floating point comparisons are splitted. Maybe we can even add red queen, so we have two roadblocks bypassing technique that are compatible, of course. We show that the combination of these two techniques may be better than using singularly one of the two techniques on some targets. We can even add a custom mutator that we run, in this case, alongside the other mutator. In this case, it is the Radanza custom mutator that you can find in the AFL++ code base that adds a mutation stage based on the popular fuzzer Radanza. You can even combine different type of instrumentation like hinogram, context-sensitive coverage, and so on, and perform cross-evaluation with your new technique based on AFL++. So that's all for the live demo. Dominik will continue the presentation.
Thank you. So, as a conclusion, AFL++ enhances comparability between different research approaches. We further improve certain parts of the fuzzing pipeline along the way. And we have a extensible Mutator API that can be used to implement research ideas in the future so that they can be mixed and matched with each other. And the best part, of course, is that AFL++ is completely open source. This concludes our talk, and we hope that you enjoyed it, and Thank you for your attention.